So this is Note Taking Guide 7.1, and we're talking about exponential growth and decay in this first little section. So you guys, exponential growth, what do you think a graph that's growing should look like?
It'll curve and then go up forever.
Yeah, like really fast go up forever, right? It's going to come like this, and it's going to come up really fast like this forever. Okay, that's the exponential growth curve. It looks like that. Okay. Does anybody know what the exponent is when you're doing an exponential growth curve? Does anybody know what that's going to look like? It's going to be like y equals e to the x, or a to the x, or k to the x, or it's going to have a power that's a variable. Okay. All right. So knowing this is what growth looks like, what do you think decay is going to look like? Down from where? It's actually going to start up really high and come down really low. Okay, its equation looks the same, but when we're talking about decay, the power is going to be negative. Okay, so it would be a negative x. So that's just a little bit of an introduction of what our curves will look like. And we're really just going to grab graphing calculators and use graphing calculators to graph them, okay? All right, so there's a couple of things you need to be reminded of in order to do logarithmic functions. And the first one is that we have a number that's called the base. Can you guys tell me what the base is of this function right here? It's 2. How come that's the base?
That's the number that you actually know is there.
Oh, because it's the only number in there? Yeah, it's the number raised to a power. That's the base, the number raised to a power. So on the next function, h of x, what's the base? 0.5. The base on the next one? 3. And the base on the last one? 10. So again, if you were going to write yourself a definition for base, what would you call it?
Number raised to power.
Yeah, I would say it's the number raised to the power. Okay, so just a review of what that is. Now, in mathematics and in science, there's a special base that occurs all of the time. That base is called Euler's number, and we represent it with the letter E. Now, you guys are really familiar with pi, right? We represent pi with that little pi symbol, and we know that that number is 3.14. Well, this Euler's number is the natural base. It happens really frequently in things that decay or grow. So that number is approximately 2.71828818. This is the number right here. It's like pi in the fact that it goes on forever without repeating and no patterns. Okay, can you guys find an E key on your calculator? It actually looks like this. It looks like e to the x. Did you find it on your calculator? It's in the little green. It's right above the ln key. And we're going to do ln in a couple of days, so look forward to that. But your e to the x key is on the calculator. We're going to show you how to use that in just a minute, okay? This is just a graph that kind of shows you how we can get the graphs to look cool. So this is the graph that we were doing like last week. This week, if we add the power to it, we can get it to have different asymptotes and different growth and decay kind of curves going on there. But we're not going to worry too much about the graphs because, like I said, we're going to do most of our graphing this unit on the graphing calculator. But what I do want to show you today is how to evaluate and how to simplify expressions with E. So this is a little matching kind of thing over here. So let's see if we can figure out how to do e to the 3 on our calculator. So we're really just going to hit that second key, hit the ln key. It always helps to turn that calculator on first. And then you just put 3 up there as the power and you get 20.08. So this one matches to that one. Okay. Questions on how to punch it in on the calculator? All right, so punch in 4e squared and see what you get. 29.55. All right. What do you think e to the negative 2 is going to be before you even do it? Anybody got a guess? Yeah, the smaller decimal point number probably. So if you do e to the negative 2, what did you get? Yeah, were you right? Yeah, you were right. And then you do 7 times e to the negative 1.
2.5.
Yeah, it's 2.575. And then 2 times e is 5.437. Questions on how to punch that in the calculator? That's a piece of cake so far, right? All right, so just a reminder then on how to deal with these if we're simplifying and not evaluating. If we're simplifying, this is going to follow the same power rules that we've learned before. So if I have e cubed times e squared, what's my answer going to be?
E to the 5th.
Yeah, e to the 5th, because we add the powers together when we multiply. Okay, over here, 4e squared cubed. All of that is being cubed. So what's your answer going to be?
4e squared and 4e to the 6.
Okay, is it 4e to the 6?
No, it's 4 e to
It's
the 2
it's 20, 36 e to the 6.
What?
All right, somebody else tell me what it is.
2,819.
That 3 has to go on to the 4, and the 3 has to go on to the 2 as the power. So what's 4 to the 3rd power? 64. And then what's on my e's? Is that 5 or 6? It is 6. It's a power raised to a power. When you have a power raised to a power, you multiply the powers. So your answer there is 64e to the 6th. All right, does anybody remember what to do with a negative power? I like to remember that a negative power kind of stands for the fraction symbol, which tells me to bring it down to the bottom of the fraction, or if it's on the bottom of the fraction, bring it up to the top of the fraction. So this actually ends up being 7 divided by e to the 1. Now, someone earlier today was like, there's a problem on your assignment that asks you to find what e is. And your calculator, when they put just e in their calculator and hit enter, it told them there was an error. What power does e have on it if there's not a power shown there? Yeah, a power of 1, right? You guys, it has to have the power of 1. I'm going to try to write my e's more like an e instead of a cursive e so you can tell that they're e's. Sorry. All right, right here. E to the negative 2 times e to the 2. What do you get when you simplify that?
Would that be e or 0?
E to the power of 0.
Because if you added another e, it'd be e to the 3rd. So would it be just plain 0?
No, that's e to the 0 because you're putting the 2 together.
You do add the 2 together, so this would be e to the 0. And anything to the 0 power is 1. Okay, so if you do it that way and do e to the 0, you could totally do that with the add the powers. Or if you wanted to do it the way we just talked about, this e squared would be on the top of the fraction. The e to the 2nd from the negative would go to the bottom of a fraction. And e squared divided by e squared is still the number 1. So you could have thought about that either direction there. But either way, when you simplify that, you still get the number 1. All right, does anybody remember what to do with division of powers? You do subtract. So you have e to the 5th over e squared, which is e to the 3rd. And if you can't remember that, you guys, you could list out your e's. You'd have 5 e's on the top, 2 e's on the bottom from your 5 and your 2. Cancel the ones that can cancel, and you're left with e3 on the top. Okay, who remembers how to do a square root?
Well, that'd be 5e to the 3rd x. Something like that.
Or something like that. That was really confident. 5e to the 3x or something like that. What do you guys think? Is he right?
Yeah, 5e cubed.
What about the x though?
5e.
Okay, I'm going to break this up into 5 times 5. Is that okay with everybody? Because that means we can bring it out. It helps us think about it that way. Could you break up 6x into 2 things that you could add together that were exactly the same? Wouldn't they be e to the 3x and e to the 3x? Do you guys agree that 3x and 3x would add together to be 6x? Because when we multiply, we add powers, right? So he was actually right. We're harassing him about that, but he was right. It's 5e to the 3x. Okay, so nice job on that. But I wanted to write it out like this anyways, just so that you could see where that x comes from. Because you look at the x and you want it to be a power of 2 there, don't you? To be able to bring it out. It kind of makes your brain think a little bit hard about it. But you really could break that up to 3x and 3x. And when you multiply those together, you would have the 6x. Okay, couple of things to just look at on the graphs. We have the graph already graphed here for us of e to the x. We're going to talk about the y-intercept. You can see where the y-intercept is at. Where's it at? 1. You can see what appears to be, you may have at least one asymptote here, but you might have 2. But if this one's coming up and going over that line, it's more than likely still going over that line, right? And if this is a growth function, would it make sense that it would keep growing? Yeah, Lacey?
You put a 0 instead of a 1.
Oh, thank you. That's funny. I do that sometimes. I say something and then I do something different. Yeah, the y-intercept is y equals 1. Thank you. So that asymptote right here, see, that's where I give away stuff because I was thinking about the next thing already. There's an asymptote right here that is binding our graph to not cross that axis. So I have an asymptote at y equals 0. But I don't have one over here. It kind of looks like there might be one, but it's actually going to continue to grow and move over. So what's the domain of this function? How far left to how far right does it go?
Infinite to infinite.
Yeah, negative infinity to infinity. And starting at the bottom and going to the top, how low does it go? 0. And how high does it go? Infinity. Good. So this is the growth function, right? Because it is growing. It's the growth function. This would be the decay function because it's that negative, e to the negative x. And you see how you start up high and then you get smaller and smaller and smaller and smaller and smaller. But eventually, what are you going to get to? 0, right? It's not ever going to cross to the negative of something that you might have. So again, the y-intercept is still the same. It's at y equals 1. The asymptote is still at y equals 0. Our domain is still negative infinity to infinity. And our range is still 0 to infinity. So they have all the same values as far as important parts of the function. They just go in completely different directions. Okay? And then this last little part right here is just an example for you to look at. That if you put a number in front of the e, then it's going to make it... Oh, it has e to the x, it has 2 to the x, and then 3 to the x. That just changes the steepness of your graph. How fast it's growing would be affected by that number that you put out in front of it.